Hi, welcome back to review tutorial on Lorentz transformations. This will be part 2. I finished up last time. I gave the matrix representations for the generators of infinitesimal Lorentz transformations. I gave S12, S23, and S31. I didn't say that the way this works, this will generate rotations around the z-axis, around the x-axis, and around the y-axis. Now I want to give the boost operators, not really operators, just matrix representations for generating Lorentz transformations. So we have S01 is equal to 0i, 0, 0, I, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. SO2. This will generate a boost, obviously, along the x-axis. S02 is equal to 0, 0, I, 0, I, 0, 0, and all zeros will be the y. S03 will be equal to 0, 0, 0, I, 0, 0, I, 0. This will generate boost on the z-axis. As I've said, finite Lorentz transformations can be obtained by exponentiating infinitesimal Lorentz transformations. There are two types: rotations. Rotations are generated from these infinitesimal generators, and they have the property that they look something like, and some orthogonal rotation matrix here that you would do in general three-dimensional mechanics. So this would be a rotation. Then we have the boost, and the boosts are a little harder to describe, and but they're generated from these generators over here. And eventually I will show that every Lorentz transformation, lambda, can be written uniquely as a product of a rotation and a boost. Let's just write this as R3. That's a three-dimensional rotation. As a four-dimensional rotation, I'll put R for these and B for these. Or in the other direction, it can be written as a B prime, R prime. And each one of these is unique. This is often not shown in many books. I don't know why. It's very easy to show, but I will demonstrate this. And right now I want to work out a general boost transformation. Might come in handy one of these days. And the rotations, the general rotations, are done in all classical mechanics books. So you can look at Goldstein to get how to look at the rotations in three-dimensional space. But the general boost will be of this form. We'll write B, and I'll have a boost parameter, which I'll call eta. And this will be equal to e to the minus I eta. Eta is the magnitude of this vector, and then I'll have the unit vector of that vector, and I'll write definitions in a second, times the three-component, times the vector matrix S. So I'm going to write, to define my terms, S is going to be a vector a vector of matrices with S01, S02, S03, and the parameters n, the vector n, is going to have parameters nx, ny, and z, and I'll also write this as eta. I'm going to say n and eta, because half the time I write my etas as n's anyway. So it's going to be eta times eta caret, and eta caret is going to be equal to eta x caret, eta y caret, eta z caret. This is just a unit vector. And eta caret dot eta caret equals 1. And so eta without a vector on top of it is just the magnitude of the boost vector. The boost vector is not the velocity vector. We'll find out the relationship. Many of you already know that the velocity is equal to the hyperbolic tangent of the boost parameter, but we'll establish that later. For now, I'm just using parameters here, and this is the magnitude, and this gives me the direction. And so all we're going to do here is we're going to do the usual expansion. This is the identity matrix, or 1 minus I eta n dot s plus I eta, should be minus I eta actually, squared over 2 factorial times n caret dot s squared plus dot dot dot. Now to evaluate this is a little bit harder than you might have come in your quantum mechanics course. Not much harder, but just a tiny bit harder. These S matrices don't have all the properties of the sigma matrices, and but it's still not hard to evaluate. The key identity that you need to show is that eta caret dot s cubed is equal to minus eta caret dot s. This is what you need to show. And you can do it either software or by hand. It's not too hard. Remember that eta caret is a univector. So we have, eta caret x squared plus eta caret y squared plus eta caret z squared equal 1. So I won't derive this. I'll leave this to you as an exercise. But when you do that, you can see how the series, this term and the cubic term go together, and the square term and the quadratic term go together. Just keep multiplying this by eta dot s. So you end up getting the boost of eta is equal to I, the identity matrix, minus I eta caret dot s times the hyperbolic sine of eta plus, minus eta caret dot s squared times the hyperbolic cosine of eta minus 1. And I'm going to write that as a matrix for you right now, just for your reference. If you actually work using these, minus I eta caret dot s is equal to 0 eta x caret, eta y caret, eta z caret, eta x caret, y caret, eta z caret, then a fat 0 over here. The next one, unfortunately, is not that nice. Minus eta caret dot s squared is equal to 1, 0, 0, 0. And the rest of it is just a matrices of etas, squares on the diagonals, and cross products on the other thing. And this matrix is symmetric. Okay. Now let's. I'm just going to show you the when you put these three things together. I'll give you the final boost matrix in terms of the eta parameters, going to be equal to gauche eta part of the reasons why a lot of books don't cover these things is because they're not that nice looking. So this is the these are the time components of the boost matrix. The spatial components, the diagonal spatial components, are like 1 plus gauche eta minus 1 times eta x squared. Don't think I left myself enough room here as usual. And then the other ones don't have the 1 on the diagonal. They just have the gauche eta minus 1 part. And again, it's cross product terms. These should all have carets on top of them. I might leave out a caret. Gauche eta minus 1 and x and y, and then this is going to be and the rest of it is the same. Okay. You can work this out yourself. I didn't do this too neatly. I'll try and do it. Next time, I'm going to convert these parameters into velocity parameters, and then I'm going to prove that theorem on the factoring of Lorentz transformations. So I'll see you on the next video. Thank you.